Good afternoon, everybody. I'd like to start this webinar with an acknowledgement to country. So AgriFutures Australia acknowledges the First Nations people of Australia as the traditional custodians of the lands and waters on which we live, learn and work. We pay our respects to past, present and future elders of these nations and any First Nations people on this webinar today. In particular, I would like to acknowledge the Ngunnawal people of Australia, the traditional custodians of the lands where I am hosting this webinar from today, which is a lovely sunny Canberra. So welcome to the AgriFutures Chicken Meat Program webinar series. It's great to have your company today. Before we get into what is the nutritional nugget of today's webinar, a little bit of housekeeping first. So we will be recording today's session and that recording has started, and this will be made available through our online channels. As I run through the housekeeping items, we will have an introductory poll that pops up on your screen with some questions, and that's just for us to gauge who's in our virtual room with us. So we'd be grateful for your responses. As this is a webinar, your audio and video functionality are not enabled, and that just means that we or our presenters can best utilize the Zoom screen real estate to view the shared content. It also means we can minimize the noise or audio distractions to our invited speaker. We will have time for questions and answers at the conclusion of today's webinar content. In the meantime, we have the dedicated Q&A chat function, which sort of sits along the bottom of your Zoom screens. So feel free to use that whilst the content is being presented to submit any questions you'd like answered. So quick introduction to myself. My name is Sarika Pandya. I'm the Research Manager, part of the broader AgriFutures Levied and Emerging Industries team. And I specifically look after the Chicken Meat Research Development and Extension Program. This webinar is part of a series in which we host expert presenters and researchers to provide you with the latest information on topics that are relevant to the industry and the program's research priorities. So today's one is all about, is a nutrition-focused webinar. So the viability of the Australian chicken meat industry, it relies on optimal health and welfare, and this is supported by a cost-efficient and environmentally responsible production system. Feed accounts for more than 60% of the total cost of chicken meat production, which makes it a major focus of research investment by the program. So this is captured in one of our key research priorities within the our RD&E plan, which is it's centered around the efficient and secure production systems. And the program invests in research and projects via the industry levies within this area, and that's just to drive evidence-based innovation in the application of nutrition principles. So today's content, it features a recently completed project delivered or led by the University of Sydney. There were some really exciting and applicable findings from this project, so I hope you enjoy today's content. So I'd like to invite our speaker, Mehdi, to turn on his camera and start sharing his screen. In the meanwhile, I will give you a little bit of introduction to Mehdi. So Dr. Mehdi Toghyani is a Senior Research Fellow and Lecturer in Poultry Nutrition and Production at the University of Sydney. He's a highly skilled and methodical animal nutritionist with proven competence in both academic and commercial settings, and has over 15 years of experience in poultry nutrition research and practical feed formulation. That's both for meat chickens as well as layers. Mehdi's authored and co-authored several scientific communications, and his current research focuses on amino acid and energy requirements, alternative feed ingredients, trace mineral nutrition, and innovative nutritional strategies to improve efficiency and sustainability of poultry production. So Mehdi will be informing us today on his project title, Optimizing Energy and Amino Acids in Meat Chickens' Diets. Quick reminder about that Q&A function, so feel free to pop in any questions along the way. Mehdi is our sole presenter today. So with that, Mehdi, I'll hand over to you to begin presenting.
Well, thank you, Sarika, for the kind introduction, and many thanks to AgriFutures Chicken Meat Program for funding the project and the opportunity to present the findings today. Hello and welcome, everyone. Today, I will be presenting and discussing the findings from the project Optimizing Energy and Amino Acid Density in Meat Chicken's Diet. I will start with a brief introduction to highlight the motivation behind this work and what led us to undertake this project. Well, we all know that growth is a function of nutrient intake, particularly the key nutrients, energy, and amino acid. And then this implies that at a nutritional balance, increasing the amino acid or energy density of the feed or increasing the intake will improve feed efficiency, or more accurately, feed efficiency corrected for FCR, corrected for body weight. But the response to increased nutrient intake is not linear, and it will eventually plateau when the birds reach their genetic potential. And it is also worth noting that these requirements, especially for the amino acids and the energy, are established for optimum performance, which based on the raw material pricing may not always yield the best economic return. Therefore, the key objective in least cost formulation is maximizing protein accretion inside the body. And we know that protein synthesis is a high energy demanding process. So at high protein intake, if we increase the supply of energy, we expect to see an increase in protein accretion or protein synthesis in the tissues until a maximum rate is reached. And providing energy beyond this point will just translate into excess body fat, which also deteriorates FCR. Therefore, the cutoff point where energy supply is just adequate for maximum protein synthesis will happen to be where we will have the maximum feed efficiency, the lowest FCR, and also the lowest nutrient excretion into the environment. But what does the literature suggest? If we go back to the published literature over the past decades or even 20 years ago, they all suggest a reduced sensitivity towards the dietary energy, which is anywhere between 100 to 200 kilocalorie, less than what the breeders have been recommending. And also, optimal amino acid density could be anywhere between 100 to 120% of what the breeders are recommending. Therefore, in line with these published literature, the breeder companies keep updating their specifications. And as you can see, over the years, the energy density, the recommendations for the energy density has been decreasing, and it's across all different phases, while the requirement or the recommendations for digestible lysine or overall amino acid has been increasing. Therefore, the objective of this project was to test if further reduction in the energy or increase in the amino acid density from the updated baseline that has been out in 2022 by the breeders will affect performance responses or how it will affect economic return in broiler chickens. So the first study for this project, which also provided the fundamentals for the subsequent studies, had 12 dietary treatments and was designed as a 4x3 factorial arrangement of the treatments. We had 4 levels of energy density, including a standard one, which followed what the breeders were recommending. And then we reduced that energy density by 50, 100, and 150 kilocalorie, with 3 levels of amino acid density following a balanced protein concept as a standard, again, based on breeder recommendation, which was increased by either 3% or 6%. The decrease in the energy and the increase in the amino acid density was consistent for each phase of the production. Decreasing the energy was achieved by decreasing the canola oil or fat supplemental oil in the diet. For example, each 50 kilocalorie reduction in the energy nearly decreased the oil inclusion by 1%. Each treatment in this study was replicated 8 times using 25 birds per replicate, and the birds were Ross 308 off-sex male birds. If we look at the body weight on day 10, you can see that both energy and amino acid density of the feed independently affected the body weight, with decreasing the energy density, increasing the body weight on day 20, on day 10, and also increasing amino acid density, increasing the body weight on day 10. The FCR was also affected by both energy and amino acid density over the starter period, but there was an interaction between the energy and amino acid density for FCR, where you can see a greater response to the higher amino acid density for FCR improvement, where we had the standard energy density compared to when we increased the amino acid density in lower energy density diets. But overall, energy reduction didn't have a meaningful impact on FCR. Even at 150 kilocalorie, FCR during the starter phase only increased by like 2 points. Then we fitted these quadratic broken line models to estimate or predict the ideal digestible lysine ratio to the energy to optimize body weight and also FCR during the starter period. And as you can see, these models estimated a digestible lysine of 1.35% to optimize body weight in the starter phase, and also close to 1.4% to optimize FCR, which both values are higher than what the breeder is recommending of 1.32%. We did and fitted these broken line models for other growth phases, but I'm not presenting those here. And if you're interested to know or have a closer look at these broken line models to estimate the digestible lysine to energy ratio for different phases, you can refer to this paper, which has been published in Poultry Science. Then body weight on day 24 was not affected by the energy density. You can see these blue bars. The body weight on day 24 was not statistically different at different energy densities, but it was affected by an interaction between the amino acid and the energy density of the feed, where at higher amino acid, both levels increase body weight at a standard ME diet. Here you can see, and but at reduced ME diets, only higher amino acid at 6% increase the body weight gain during the body weight on day 24. FCR was impacted by the energy and amino acid density independent of each other. As you can see, decreasing the energy density, especially at 100 kilocalorie and 150 kilocalorie, increased the FCR during the grower period, and increasing the amino acid density, again, independent of the energy density, resulted in an improvement in FCR. Body weight on day 35 was not affected by the energy density of the diet, but was affected by an interaction between the energy and amino acid density. Again, we had a greater response in body weight at both medium and high amino acid density when we had the standard ME density diet compared to the reduced ME diets. As you can see, an increase of 130 gram in response to 6% increase in amino acid density at a standard energy density, but at lower energy density, the response or the increase in body weight was lower. Similarly, FCR over the finisher period was affected by an interaction between the energy and amino acid density of the feed, where at high amino acid density, only at a standard energy density, we see an improvement of close to 6 points in FCR, a very sharp improvement. But in reduced ME diets, FCR only improved by around 2 points in response to higher amino acid density in the diet. The final body weight on day 42 was not affected by the energy and remained statistically the same between different energy treatment groups, but it was impacted again by a interaction between the energy and amino acid density, where we had a greater response for body weight at both medium and high amino acid density here when the birds received the standard, the standard ME density diets compared to when we reduced the energy density. And the FCR over that last week after trial, the withdrawal period was affected by an interaction between the energy and amino acids, where we see an increase in FCR in response to higher amino acids only at a standard ME density, but at lower ME density, the FCR remains statistically the same and does not go up or down in response to higher amino acid density. But overall, this phase looked to be more sensitive to the energy reduction, at least in terms of the FCR. And as you can see, 50 kilocalorie reduction in the energy increased the FCR by nearly 10 points. The overall feed intake and the FCR for 0 to 42 day was affected by the energy and amino acids independent of each other. Decreasing the energy density increased the overall feed intake, and increasing amino acid density also increased the overall feed intake. But the FCR was affected by an interaction between the energy and amino acid density, where FCR improved in response to higher amino acid density at both medium 3% or high 6%, only at a standard energy density. But at reduced ME, FCR was only statistically improved when the birds were receiving the high amino acid density diets and not the medium ones. Looking at the overall FCR, you can see that each 50 kilocalorie reduction in the energy, when it is consistent from the starter all the way to the withdrawal phase, can cost nearly 2 points of FCR. But the age to 2.5 kg was not affected by the energy density of the diets, and increasing the amino acid density actually accelerated the growth and shortened that age by nearly half a day when we increased the amino acid density by 3% and almost 1 day when we had 6% increase in the amino acid density, and that was independent of the energy density of the feed. We used market pricing for the ingredients at the time of formulation to formulate these diets. And as you can see, reducing the energy density of the diet resulted in a linear reduction in the feed cost per kg of body weight, and increasing the amino acid density, despite the improvement in the growth rate, higher body weight gain, and better FCR, still translated into a higher feed cost per kg of body weight. Breast meat yield was independently affected by both the energy and amino acid, where reducing the energy density increased breast meat yield, and increasing the amino acid density also increased the breast meat yield. Similarly, fat pad weight was independently affected by the energy and amino acid density. Reducing the energy density reduced the fat pad weight, and increasing the amino acid density, also independent of the energy density, reduced the fat pad weight. Woody breast scores were not affected by the energy density of the feed, but rather affected by the amino acid density, where increasing amino acid density resulted in a higher score for the woody breast. But the white striping scores were affected by both the energy and amino acid density. Reducing the energy density reduced the occurrence of white striping, and increasing the amino acid density increased the white striping scores in the breast fillet. Nitrogen digestibility or crude protein digestibility was not affected by the dietary treatments, but nitrogen excretion in the feces was affected by the amino acid density, where increasing the amino acid density resulted in higher nitrogen excretion. Fat excretion also decreased when the energy density of the diet decreased, but it was not affected by the amino acid density. But interestingly, despite that reduced fat excretion, when we reduce the energy density of the diet, ileal fat digestibility also reduced. The overall energy digestibility was not affected by the dietary treatments or the interaction between energy and amino acid density, but starch digestibility was affected by the amino acid density of the feed, where we saw a higher starch digestibility in response to higher amino acid density in the feed. And we would have expected completely the opposite, because both starch and amino acids rely on sodium-dependent transporters to enter the enterocytes in the gut, and could be competing for sodium, but apparently in this study, sodium availability was not a limiting factor for either starch or amino acid digestibility. Then calcium excretion was again independently affected by the energy density and amino acid density, where in decreasing the energy density, decreased calcium excretion in the feces, and also increasing the amino acid density reduced the calcium excretion in the feces. There was no effect of treatments on phosphorus excretion. Manganese excretion was only affected by the energy, where decreasing the energy density resulted in less manganese being excreted in the feces. Similar for the copper, reducing the dietary energy density resulted in lower copper excretion in the feces. Iron excretion was affected by the amino acid density, where increasing the amino acid density reduced the concentration or excretion of the iron in the feces. Zinc excretion was not statistically affected by the dietary treatments, but you can see there was still a linear decrease in zinc concentration in the feces when the dietary energy was reduced. So for more details and discussion on the nutrient intake, digestibility, and excretion, you can refer to this paper, which was published in Poultry Science. Then based on the results that we obtained in the first study, we decided to design the second study. We saw that the younger birds during the starter and grower phase are less sensitive to the energy reduction. So we decided to test if we can reproduce the similar results if we decrease the energy density by 100 kilocalorie in the starter and 75 kilocalorie in the grower phase. And based on what the quadratic broken line models estimated we would need a higher digestible lysine to optimize FCR and body weight in the starter, and also higher digestible lysine concentration or amino acid concentration compared to what the breeders are recommending to optimize body weight and FCR during the grower phase. And we again here in these two treatments, we wanted to see if the response to the 50 kilocalorie energy reduction in the finisher is an increase in the FCR, and what happens if we increase the the energy density in the withdrawal phase, where the birds seem to be more hungry for the energy and craving more energy. So we increase the energy density by 50 kilocalorie in these three treatments. So the first treatment followed the breeder recommendations for both the energy and amino acid density. Here again, each treatment was replicated 8 times, and we used 25 birds of Ross 308 sex male birds per replicate. If we look at the body weight on day 10 and the FCR for the starter period, you can see that none was significantly affected by the dietary treatments here, where we decreased the energy density by 100 kilocalorie. FCR was comparable and the body weight was not statistically different. The higher 4% amino acid density slightly improved body weight, not in all treatments, but in some of the treatments, but didn't seem to have any effect on the FCR during that starter phase. Body weight on day 24 was not affected by the dietary treatments, and reduction of the energy in the grower phase also yielded similar body weight, but FCR was affected by the dietary treatments, and similar to what we had seen in the first trial, you can see increasing the amino acid density resulted in 2.5 to 3 points improvement in FCR over the grower period. Body weight on day 35 was not affected, and then that reduction of the energy density early on didn't translate into any loss of body weight or increase in FCR. But here again, when we reduce the energy density during the finisher phase by 50 kilocalorie, that 50 kilocalorie translated to a higher FCR, which is very similar to the first study, was around 2 to 2.5 points of FCR. The final body weight on day 42 was not affected by the dietary treatments, neither was the FCR over the withdrawal period, and that extra kilocalorie of 50 kilocalorie that we put into the withdrawal diet was not really translated into any improvement in FCR, at least statistically. And the feed intake was not also affected by the dietary treatments. As discussed, final body weight on day 42 was not affected by dietary treatments, and the corrected FCR for 0 to 42-day period was not affected by the dietary treatments. Especially if we focus on the first 3 treatments, you can see that 100 kilocalorie reduction in the energy density of the starter and 75 kilocalorie in the grower didn't compromise body weight or the FCR. Numerically, this T5 recorded the highest body weight and the best FCR. And that T5 was where we had that 100 kilocalorie reduction in the starter and 75 kilocalorie reduction in the grower. No changes to energy or amino acid density in the finisher, but 4% higher amino acid density in the starter and 50 kilocalorie higher energy density in the withdrawal phase. Again, the results and findings from this study have been published in this paper. So if you want to have a closer look on the cost efficiency and also carcass quality, you can refer to this paper, which has been published in the Journal of Applied Poultry Research. Then based on the results that we saw in the first study and also the second study, where decreasing the energy density by 100 kilocalorie in the starter and 75 kilocalorie in the grower doesn't really compromise the final gross performance, especially in terms of feed cost, FCR, or body weight gain. But those two previous trials, we had used only wheat-based diet and canola oil as a supplemental oil in the diet. Here in the third study, we wanted to see if changing the grain source or the supplemental oil source will affect the bird's response to those lower energy diets, especially in the starter and grower. So this study was designed as a 3-by-3 factorial arrangement of the treatments, where we had 3 grain sources of wheat, sorghum, and barley, and 3 fat sources of canola oil, poultry tallow, or beef tallow. The energy was reduced by 100 kilocalorie in the starter and 75 kilocalorie in the grower compared to what RUS 308 guidelines or recommendations are, but we followed the similar digestible lysine density. In the sorghum-based diet, we use 10% wheat across all the 4 phases in the diets just to maintain pellet quality, and barley inclusion followed an incremental program where we had 15, 25, 30, and 35% of barley in the starter, grower, finisher, and withdrawal diets, respectively. Body weight on day 10 was not affected by the grain source or the fat source or the interaction between grain and fat. And as you can see, FCR during that starter period was almost identical and very close for each of these treatments and not affected by the fat, grain source, or their interaction. Similar results were observed for body weight on day 22 and FCR during the grower phase, which neither were affected by the grain source, fat source, or an interaction between grain and fat source. This confirms that reducing the energy density by 100 kilocalorie in the starter and 75 kilocalorie in the grower phase will generate similar results in sorghum-based diets or barley-based diets and is independent of the supplemental fat source. There was no main effect of the fat source for any performance parameters at the end of the study, but here, as you can see, although not statistically significant, but body weight on day 42 was slightly by around 50 grams per bird higher in birds receiving the wheat-based diets compared to sorghum or barley-based diets. But the final FCR was statistically affected by the grain source, and as you can see, feeding the sorghum-based diets increased the FCR by around 2 to 2.5 points compared to feeding the wheat-based diets. And the barley-based diets were in an intermediate position. The overall feed intake, again, was not statistically affected by the dietary grain source, but barley-fed birds had a lower feed intake compared to sorghum or wheat, and the age to 2.5 kg of body weight was not statistically affected by the grain source, but again, you can see that numerically, those birds on the wheat-based diets grew at least by half a day faster than those receiving the sorghum or barley-based diets. Interestingly, starch digestibility was affected by the grain source of the diet, where we had lower starch digestibility independent of the fat source in sorghum-based diets. This could partly explain the higher FCR of 2 to 2.5 points that we observed with sorghum-based diets. And the results and findings from this study have been published in this paper. And if you're interested to have a closer look on the nutrient digestibility, carcass characteristics, and the specific performance metrics during each phase of the study, you can refer to this paper. Then the fourth study, or the final study for the project, was designed as a 3x2 factorial, and we decided to test that low energy starter and grower diets against the RAS recommendations and COP recommendations in both RAS or COP. So we had 3 dietary specifications followed. The first one followed RAS recommendation, COP recommendations, and the AgriFuture specs. That was the lower energy density in the starter and grower. We call it here AGF specs, tested in 2 breeds, either RAS 308 or COP 500. But in this study, each treatment was replicated 8 times, and instead of using male birds, we used straight-run mixed-sex birds, but 45 birds per replicate pen. I'm only presenting the results for the final body weight and the corrected FCR for 0 to 42 day. As you can see here, the body weight was not affected by the diet specification, but was only affected by the breed, and cub birds grew faster and put on more body weight compared to the RAS, and at day 42 were on average like 200 grams heavier than RAS, but FCR was affected by both the breed and also diet specification, and this is corrected FCR. As you can see, cub birds recorded a higher FCR, and cub specification resulted in a higher FCR, while the AgriFuture specs generated similar results whether it was fed to cub birds or to RAS, and it was comparable between RAS specification in both breeds. The overall feed intake was also affected by both the breed and the diet specification, where cub birds had a higher overall feed intake, and cub specification, regardless of the breed, resulted in a higher feed intake. But the feed cost per kg of body weight was affected by an interaction between the breed and diet specification, where you can see feeding the RAS specification to the cub birds resulted in the highest feed cost per kg of body weight, but feeding the cub specification to RAS resulted in the lowest feed cost per kg of body weight. And the AgriFuture specs generated identical feed cost per kg when they were fed to cub birds compared to cub specification, and when fed to RAS, the AGF specs actually reduced the feed cost per kg of body weight by 4 cents compared to RAS specification. Then we did some modeling and fitted regression models to predict the body weight gain and FCR in response to both the dietary EMI and digestible lysine concentration in the feed, and also the intake for different growth phases. We used the data for body weight gain and FCR values only from the first 3 studies, where we had male birds on wheat-based diets with canola oil. We did both univariable and multivariable regression models, but I'm just reporting the multivariable regression models here. As you can see, to predict body weight gain, the ME and digestible lysine concentration or density in the feed was not a strong predictor for the body weight gain. But when we plugged in the actual digestible lysine and energy intake, the accuracy of the models improved by a lot. and we had an average R square of 0.5. So how does this model actually work? I will give you an example for a grower feed from day 10 to 24, and we consider an average intake of 110 grams. So at that intake, if we increase the dietary ME density by 50 kilocalorie in the grower phase, the ME intake will increase by around 5 kilocalorie per bird per day. And then at that similar intake, if we increase the digestible lysine concentration in the feed by 100 milligram or 0.1%, that will increase the digestible lysine intake by around average of 10 milligram per bird per day. So having a constant lysine intake, increasing the ME intake by 5 kilocalorie, you can see it will result in an average of 10 gram higher body weight at the end of the grower phase or on day 24. But having constant energy intake, but only increasing the digestible lysine intake will also increase the body weight gain or the final body weight by around 25 gram per bed on day 24, but concurrent increase in energy intake by 5 kilocalorie and an extra 10 milligram of digestible lysine. When I'm talking about digestible lysine, I mean in a balanced protein concept. So all the other essential amino acids have moved up relevant to the lysine density. So that 10 milligram higher digestible lysine, when combined with the higher energy intake, can generate an increased body weight of 30 gram per bed in that grower period. Opposite to what we saw for the body weight gain, to predict the FCR in response to dietary ME and lysine concentration or intake, the actual concentration in the feed was a more accurate predictor compared to the actual intake. Of course, the accuracy decreased as the birds were getting older, and we had an R square of 0.44 in the starter, which went down to 0.13 in the withdrawal phase. Here again, if we increase dietary ME density, so we're not talking about the intake, only increase dietary ME density by 50 kilocalorie, and then at constant digestible lysine density, we would expect around 2 points improvement in FCR. But at constant ME density in the feed and increasing digestible lysine density by 0.1% or 100 milligram, we would expect a 4 points improvement in FCR, and concurrent increase in the energy density of the feed combined by increasing the digestible lysine density of the feed, the FCR, the predicted FCR improvements could be as high as 6 points. Okay, I will wrap up this presentation by some key point summary, just summarizing what I presented here. Reducing dietary ME by 100 kilocalorie in the starter and 75 kilocalorie in the grower feed has got the potential to lower the feed cost without actually compromising the performance or carcass traits. And it works irrespective of the grain source or fat source, and also the breed. But the ME reduction in the older birds will increase the feed intake, and every 50 kilocalorie reduction in the ME due to the increased feed intake will cost around 2 points of FCR. But this will improve the carcass leanness and also will reduce the white striping frequency. Reducing dietary ME also decreases nutrient excretion as discussed, like fat, calcium, and copper, and potentially zinc. And higher amino acid density improves growth and also FCR, but must be balanced but we must actually balance the performance gains against the feed cost. The interaction between the energy and amino acid density that we saw from the results from the first study suggests that at higher amino acid density, we need to have a higher supply of energy to be able to harvest the full potential of the diet or to maximize that protein accretion. Therefore, precision nutrition enhances both economic and also the environmental outcomes for chicken meat production. RAS 308 showed better feed efficiency, while COP 500 had a faster growth rate, and the AGF specs or the optimized ME density, that reduction in the starter and the grower for the ME density works effectively for both breeds and can help us to minimize the feed cost per kg of body weight. And the regression models using both the energy and digestible lysine will improve the accuracy for predicting body weight gain and FCR. And at the end, I would like to thank AgriFuture Chicken Meat Program again for funding this project, and also our lovely technicians at PRF who helped running the feeding trials, and our PhD student, Karia, who completed the second and the fourth study of this project, and also Jojo, who completed the third study of this project. Thank you very much for your attention, and I'd be happy to take on any questions if there is any question.
Thanks very much, Mehdi. I'll just get you to keep your video on. Oh, let me turn mine on as well. Thank you very much for distilling a lot of work into thereabouts 40 minutes, having worked with you on this project across the last 3 years for our audience on the webinar. I think Mehdi could give a very detailed webinar of about half a day of all of the trials that were conducted. Part of this work's no mean feat to reduce it down into this short period of time. Look, we did have a couple of questions come through the chat. If there are any more burning questions, feel free to keep putting them in there. We'll keep asking Mehdi as many as we can till we get to our hour mark. So Mehdi, first question that was received, it was a question of many questions, so I'm going to break it up into a couple of parts for you. First part, is it common practice to include both phytase and xylanase enzymes in Australian type wheat-based diets?
It is very common. Especially most of the producers now are using a high dose of phytase, above 1000 FDU, and xylanase is a must in all wheat-based diets. So I didn't present, because of course didn't have the time, the diets, but all these diets had a straight xylanase, supplemented at the recommendations, following the recommendations of the manufacturer, and we had 2000 FYT of the phytase in all these diets for all the 4 studies.
And then the follow-up questions to that was how much were the uplifts on ME that were assigned to phytase and or xylanase that might dictate the requirements of this. Did you use ME or AA uplifts for phytase for these diets during the formulation?
Yeah, for xylanase, we NIR scanned all the ingredients, and then what the NIR was suggesting for the energy of the wheat, we increased that by around 3 or 3.5%, but didn't apply any uplift in response to xylanase to the other ingredients in the feed. And for phytase, for that 2000 FYT, we considered an uplift in the energy of the total diet by around, that was 30 kilocalorie of energy.
Alrighty, and then we did get another question about the reduced dietary ME levels. So at those reduced levels, when extra amino acids were added and improved the body weight gain, how did you know whether these extra amino acids were not used as an energy source after being deaminated? And did you look into
Well,
blood plasma urea or any other amino acid biomarkers?
no, we didn't look at that, but the interactions between the energy and amino acid density of the diet suggest that at very low energy density, like when we reduce by 100 or 150 kilocalorie, the response to the higher amino acid density was not as big as what we saw under the standard ME density. So there is the possibility that the energy supply might have not been enough, and part of that, the extra amino acids or protein that was supplied in the low energy diets could have been utilized as a source of energy. But unfortunately, no, we didn't look into any biomarkers to verify this.
I think that brings us to the end of the questions that we've been asked in across the chat and the Q&A function. I think I'd scribbled down a couple of the groupings of the key findings. So over this sort of 3-year study, it sounds like a lot of your key findings, if you were to group them into sort of themes, you've got sort of efficient, a piece on efficient feed formulation, cost-effective nutrition optimization, some findings related to grain and fat source utilization, as well as those Ross and Cobb specific strategies. And I guess that all leads to a nice sort of sustainability piece, both from, by the looks of it, from an economical as well as that environmental lens. And it's really nice to see how you've used that predictive modeling to deliver precise or detailed ME and amino acid recommendations for each of those growth phases. And hopefully that offers the industry and nutritionists a robust basis to formulate those high-performing diets, and very importantly tailored to the Australian conditions. So I guess if there's no further questions, I'm just double checking there's nothing there in the chat that has been put in. What I'll do is I'll begin the close up for the closing of this webinar. So I'd like to bring your attention to a post-webinar survey that will pop up on your screen somewhere. And we do greatly appreciate your time in providing the feedback to these few questions. And we do look at these following the webinars to see how we can improve or feature content that is identified as important to the industry. Just a quick reminder that we will provide the links to the resources mentioned during this webinar following the webinar, along with the recording. For anybody that is here on the call, you will see it in the chat. So that includes the links to the 4 published papers, as well as the published full and shorter snapshot report that's come out of this research. I'd like to extend a big thank you to Mehdi. It's been, like I've said a few times, it's been really great working with you over the last few years, and we appreciate your time in distilling and sharing the findings from the research that you've completed. And of course, would like to thank everybody who has registered and those who have joined today. Look, I'd like to wish you a fantastic rest of your Thursday, and we shall see you next time. Bye for now.